All right, picture this. You're standing on the floor of a massive, modern shipyard. Right above you, a cutting head zips across this enormous plate of steel in a highly complex, winding path. Sparks are flying, the metal is glowing, and in exactly 40 seconds, a perfectly shaped, intricately angled structural bracket just falls away. It's a flawless cut. But you know what the absolute craziest part is? Not a single human hand touched it. And not a single human mind had to make a decision about where that cutting path should go while it was happening. So let's dive into this, because today we're exploring the awe-inspiring world of modern shipyard machining, where digital code translates directly into physical giants of the sea.
Zero human decisions. That really is the key to all of this. I mean, in the past, ship design meant these vast halls filled with armies of draftsmen hunched over paper drawings, which then had to be manually interpreted by workers on the factory floor. Today, that entire sequence of human interpretation is just gone. That mesmerizing, autonomous movement of the cutting head we just talked about is driven entirely by a digital computer design sent straight down a cable to the machine. The digital model literally becomes the physical steel, with zero human transcription errors along the way. It's pretty wild.
So to understand how this actually works, we need to look at the brain of the operation, NC, or numerical control. Numerically controlled cutting simply means that the machine's movements are commanded entirely by numbers. The machine doesn't interpret a drawing or look at a blueprint. Instead, it acts as a bridge. It takes the ship product model, which is this massive 3D database containing every single piece of information about the ship, and it translates it into physical reality by following a precise sequence of XY coordinates.
And the workflow is incredibly fast. Step 1. The naval architect engineers the part in the CAD software. Step 2. The software automatically extracts the XY coordinates for that specific geometric shape. Step 3. Those coordinates are fed straight to the cutting machine, which slices the physical steel. Draw it once, build it directly. Since there's no human transcription, there's no rework from a misread drawing. It is pure, uninterrupted data flowing from the mind of the designer straight to the steel.
Section 1. The workhorse oxy-fuel gas profilers. When you need to cut through the massive, ultra-thick plates that make up a ship's keel, this is the machine you call. The really crucial thing to understand about oxy-fuel cutting is the fiery chemistry behind it. It doesn't actually just melt the steel. First, a preheat flame brings the steel up to its ignition temperature. Then, the machine blasts a high-pressure jet of pure oxygen directly at it. And this triggers a massive exothermic reaction. The iron in the steel literally reacts with the oxygen and burns. This reaction generates enough of its own heat to sustain the cut all the way through those incredibly thick, heavy shipyard plates. It's economical, it's powerful, and it is absolutely the workhorse of heavy plate cutting.
Section 2. The speedster, plasma arc paying.
But what if you don't need to cut heavy keel plates? What if you're working on medium-thickness hull plates and you need it done fast? Well, that's when you bring in the plasma arc cutter. Just wrap your head around that number for a second. 20,000 degrees Celsius. Plasma arc cutting works on entirely different physics than oxy-fuel. It ionizes a gas into a plasma jet that reaches mind-bending temperatures. We're talking hotter than the surface of the sun. Instead of burning the steel through a chemical reaction, this superheated column of plasma simply melts its way through the metal in an absolute flash.
Seeing these two methods head-to-head is super fascinating. Oxy-fuel burns the steel, which is great for thick plates, but, it's a bit slower. Plasma melts the steel. It trades the ability to cut extreme thicknesses for incredible speed, and because of this speed and the precise nature of the plasma jet, it produces a narrower kerf, which is just a fancy term for the width of the cut. That means less wasted material and, crucially, less distortion from heat. All of that makes plasma the go-to method for most of the medium-thickness structural plates on a ship.
Section 3. The scalpels, laser, and water jet. Sometimes speed and raw power just aren't enough. Sometimes you need a literal scalpel for highly complex geometries, delicate pipe penetration rings, or materials where superior edge quality is absolutely paramount. These two technologies achieve that exact precision, but in completely opposite ways. The laser uses a highly focused beam of light to literally vaporize the steel. It's extremely precise and leaves a very narrow cut. The water jet, on the other hand, cuts using an ultra-high-pressure stream of water mixed with abrasive particles. It blasts through the material at 2.5 times the speed of sound. And the craziest part? The water jet does this with absolutely zero heat. And that actually brings us to a massively important concept in shipbuilding, the heat-affected zone, or HAZ. You see, whenever you cut steel with extreme heat, like with an oxy-fuel flame or a plasma arc, the region right next to the cut gets superheated.
This heat actually alters the microstructure and the mechanical properties of the steel in that specific zone, potentially weakening it or changing how it bends. And believe me, shipbuilders care deeply about this.
This comparison right here reveals exactly why matching the right tool to the job is so critical. Oxyfuel gives you the widest heat-affected zone. Plasma is narrower. Laser is very narrow. But the water jet, because it is a cold-cutting process, it leaves zero heat-affected zone. Literally zero. This is exactly why, even though water jet cutting is more expensive and slower, it is absolutely essential when cutting heat-sensitive composite materials, high-strength alloys, or really any part where heat distortion would ruin the structural integrity.
So let's pull back and look at the big picture. Shipyard production planners use this exact matrix to optimize their build. They look at the part required and evaluate. Okay, what is the thickness? How fast do we need it? How perfect does the edge need to be? And how much heat can this material actually take? Heavy keel plate? Oxyfuel. Standard hull plating? Plasma for speed. A complex, delicate structural bracket? Laser. Heat-sensitive alloy? Water jet. It is a perfect synchronization of tool and task.
But here is the real magic of this whole operation. Whether it's a roaring oxyfuel flame burning through iron, a 20,000-degree plasma jet, a vaporizing laser, or a supersonic blast of cold water, every single one of these wildly different physical tools obeys the exact same digital master. They are all driven by the centralized ship product model. The software tells the production planner which method to use, and the machine executes the CAD geometry flawlessly.
Now, cutting this steel is really just the beginning. We've transformed our digital code into a massive stack of perfectly cut, perfectly sized flat plates. But obviously, ships aren't boxes, right? Almost nothing below the waterline is flat. These rigid, two-dimensional pieces of steel now have to be forced into the beautiful hydrodynamic three-dimensional curves of a ship's hull.
Which leaves us with something pretty fascinating to think about. We have seen how decades of manual drafting and human transcription have been entirely replaced by a seamless flow of data from a naval architect's screen directly to a 20,000-degree plasma jet, executing cuts with zero human decisions. If a machine can flawlessly slice the pieces of a massive ocean leviathan directly from a digital file today, what physical boundaries will autonomous manufacturing conquer tomorrow? The gap between the digital imagination and physical reality has literally never been thinner. Thanks for joining me on this explainer, and keep your curiosity sharp.